the base and the number that's inside the log. So this is called the base of the log. So you're asking 5 to what power would give me 125. So the value of this log function is just 3. And that's because 5 cubed equals 125. So it's kind of like solving a puzzle. This is the base of the log. You have to raise it to this power to get the number inside the log. So if 2 is your base, what do you have to raise to get 1/8? So you've got to cube it and flip it over, right? So -3. So 2 to the -3rd power would give me 1/8. So a log is just another way of representing an exponential relationship. They end up being inverses of each other, logs and exponents, so they will undo each other. What would you say for number 3? These are a little bit more challenging because they're using fractional exponents and negative exponents. So 36 to what power would give me just 6? Huh? Not 2. That would be if 6 was here. So this is question mark. 36 to what power gets me back down to 6? So how are 36 and 6 related? But you have to put the power on the 36. Yep. 1/2, because that would be the square root of 36 gets you back down to 6. So it would have to be a fractional exponent of 1/2. All right, so what would you say for number 4? 4 to what power gives me 64? Is this clicking for you? Did some of you go through and do it during the end of the quiz, or are you just looking at it now? I know there was a video last week, but this is kind of new. So 4 to what power will give me 64? What would you say for number 4? Nat? 3. 4 cubed is 64. What would you say for this one? So 27, I have to raise it to some fractional exponent, and it has to get me down to 9. So what base or what power family are 27 and 9 both a part of? It's the power of 3. So you have to go down the cube root first, right? That gets you down to 3, and then 3 squared is 9. So it would be the, what did we just say, the 2/3 power. Cube root of 27, and then 3 squared is 9. So 2/3 power. So something that's a little bit different here is there's no base. So the rule for it's called a common log. So if there's no base on a log, the base is 10 that's sitting there. And it's just like a square root function. When I write square root, I don't have to write a 2 to know that it's a square root, but I do have to write like a 3 if it's a cube root. So if it's a common log, you know that the base is 10. So it would be just 2, right? Because 10 squared gets me to 100. So the log of 100 is 2. I just want to show you on your calculator that you have a log button. This is not very in focus. So do you see where the log button is on the calculator, LOG? That log button has a base of 10 and only 10. So if you type the log of 100, it's going to be able to evaluate that and tell you that the answer is 2. But if you want to type in like the log base 5 of 25, if you just type the log of 25, it's not going to do it for you because that's the base 10. So it's actually under, I want to show you where the log button is. It's under math. And then I think it's way down at the bottom. See how choice number A is log base? So math and choice A gets you to a different log key where you get to choose the base and you get to choose the number inside. So for example, if I wanted to do the log base 5 of 25, then it'll tell me my answer is 2. So make sure that you're using the right log button, but these should all be mental math. All right, so this one was 2. What about number 7? I skipped it. 3 to what power is itself? 1, right? So 3 to the first power is 3. 8 squared would be 64, so the answer to number 9 would just be 2. 2 to what power is 16? You can count them up on your fingers. 2 times 2 is 4, times 2 is 8, times 2 is 16, so it would be the power of 4 for that one. How do I take the reciprocal of 11? So 11 to what power would give me 1 over 11? -1. So see how you need your exponent skills to be able to do logs. 3 to what power is 81? 3 times 3 is 9, times 3 is 27, times 3 would be 81. So the fourth power. And, you know, if you didn't know that one, you could figure it out by just multiplying your powers of 3. Let's see, 2, and I have to get to 128. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, so times 2 is 128, and I just did 7 of them. So you could check, though, just that 2 to the 7th is 128 on your calculator. Oh, shoot, I repeated question 6, right? I should have changed that one. Number 15. This time I've got 25 as the base and 5 as the number inside. So what is going to be the value of that log relationship? What would you say? How do I go from 25 down to 5? 1/2. It's the square root of 25 to get 5. All right, what about 16? So I'm starting at the number of 2, and I have to get 1 over 4. So I would have to square 2 and flip it over. So it sounds like a value of -2. 2 to the -2nd power. And then anything to the 0 power is 1, right? So log base 15 of 1 just has to be 0. And then 18, 9, I have to get to 1 over 81. So I'd have to square the 9 and flip it over. So -2. Are you with me kind of on that relationship? So it's a new function that you've probably never used before. The definition of a log function basically is the exponential relationship. So y equals log base a of x, if and only if x equals a to the y power. So the base raised to this power gives me the number that's inside the log. And then this should say x cannot be 0. So can you change that little multiply sign in the definition? X can't be 0, a can't be 0, or sorry, a can't be 1, and a can't be 0. I don't know why that changed the symbol. Something about Microsoft Word, I think. Okay. And then at the bottom there, log functions are the inverse of exponential functions and vice versa. A logarithm is just an exponent. So, you know, log base 2 of 16 equals 4. It just means that 2 has to be raised to the 4th power to get 16. So 2 to the 4th is 16. You just have to kind of remember that circular relationship, and the base of the log is always the base of the exponential expression. So the base of a log and base of an exponent, there's a reason they're both called the base of the problem. All right, so this is just evaluating some more logs. So now that we did the warm-up on the front page together, I'd like you to try 1 through 4. So just what do those equal? And I'd like you to also try 5, 6, and 7. So you're just rewriting that expression in log form. So for example, if I was going to do number 5, it would be that the log base 4 of 16 equals 2. So you have to be able to convert between exponential and log form very fluently. So I'd like you to try 1 through 7 kind of on your own now that we've done the front page. So being able to evaluate logs is kind of your first step in understanding logs. Being able to just write it as exponential or log expressions is very important when we start graphing them, finding the inverse, solving. So you just have to be really fluent between how to read an exponential, right? 2 to this power equals this number. And then same with a log. 2 to this power equals this number. So it's the same relationship, just written in a new way. And you've seen other things that could be written in different ways. For example, the square root of x is the same as writing x to the 1/2 power, right? So it's the same value, just written in a different way. I had already talked about this a little bit on the front page, but common log is just written as log. It has a base of 10. Natural log is another key on your calculator. So under the log button is the natural log button, LN, so natural log. It has a base of E. So we're going to see this a little bit when we start solving real life problems, because E is the natural base and it's used for compound interest. It's used for growth. So we're going to see this log button used quite a bit when we do application problems. So on 8, 9, 10, and 11, I just wanted you to use the regular log key and the regular natural log key to just evaluate those. Those would be without a calculator. So just take a minute and try. You could actually try 8 through 13. There's something called a change of base formula for the old-fashioned scientific calculators, but we could just go to the math key on our calculator and do choice A, log base. So if you want to try that key and evaluate up through 13. So try 8 through 13 on your calculator. Round to what? 2 decimal places, it says. Someone's going to watch this. All right. So to find an inverse, we remember that our first step is to just switch x and y in the problem, right? We're just going to do some algebra here to solve the inverses. Let me just refocus. So you take x and you make this 6 to the y power. So all I've done is I've found the inverse by switching x and y, but I always want to write a function as y equals. So if you start as exponential form, you want to rewrite this function in log form, because the inverse of an exponential function will always be a log function. So if I rewrite this in log form, the base was 6, so now I have log with base 6, and isn't it 6 to the y power equals x? So it would be log base 6 of x equals y, so that's 6 to the y power equals x, 6 to the y power equals x. So these two in purple should be equivalent expressions for logs and exponents. The two in purple are different from the starting function, because the starting function had y equals 6 to the x. This function is x equals 6 to the y. So this is my inverse function. If you want to write it as y equals log base 6 of x, but this is y equals 2. So a base 6 exponent has a base 6 log as its inverse function, just like square root and square, or cube root and cube, or addition and subtraction. Logs and exponents undo each other. So on this one, you would kind of do the same thing. So x equals 4 to the y power plus 1. This is not quite ready to turn into log form yet because of this plus 1. So before you turn it into log form, you need to get the exponent by itself. So x minus 1 equals 4 to the y power would be your next step. And then this is an exponential equation that you're going to rewrite as a log equation. So if the base was 4, this is going to be a log base 4 function of x minus 1 equals y. See how this is 4 raised to the y power gives you x minus 1, and you freed up y from the exponent. So this is the y equals function. If you want to rewrite it in the right order, you can, but if y is by itself, it's a function. So it's interesting that this plus 1 shift was up 1, right? What's this shift for a log function? Right 1. So up 1 for an exponential function and right 1 for a log function are going to be inverses of each other. And I'll show you why that is when we start graphing them. All right, let's do the last one. So x equals 2 to the y minus 3. It's already by itself on the exponent side, so I'm just going to switch forms. If the base is 2, it's going to be a log base 2 function of x equals y minus 3, right? We're trying to get the y by itself, so the y should end up over on the equal side. So what would be my last step to finish this, to get y by itself? Add 3 to the other side. So I'll write it y equals log base 2 of x plus 3. You're really adding the 3 on the outside of this log function. So there, that time I wrote it as a y equals function. So that's a really hard concept to understand. So if you're even just starting to understand how x and y and logs and exponents are related in inverses, that's a good first step. But for me, when there's no numbers involved, it's a challenging conversion of the two exponent and log equations. So I'm just going to show it to you in the other direction. So all of these started as exponents. They all ended as logs. The last 3 I want to look at today are logs. So 17, 18, and 19 all start as logs. They're all going to finish as exponents because they're inverses of each other. So your first step is to switch x and y. So x and y have just been switched. That's it. You need to have a base. So what is the base of the natural log function that we said? E. So I'm going to write the base there so that I can see what the base is in this problem. If the log function is by itself, I'm ready to rewrite this in exponential form. So the base is e, so this is an e to the x exponential function. So e to the x equals y plus 3. E to this power is equal to what's inside the log. So my final function would be y equals e to the x minus 3 to get y by itself. So see how I'm ending with an exponential function, but I started with a log function. And e to the x is just an exponential graph, right? It looks like 2 to the x. It's just 2.7 instead of just 2. Shifted down 3. This one was shifted to the left, right? The log function shifted to the left by 3. Its inverse is going to be an exponential function shifted down 3. So they're related in that way. 18, I switch x and y. So I don't switch anything else. You just switch x and y. You get the log function by itself first. So I'd have to first add the 5 to the other side. I need to put a base in this problem. So what is the base of a log if it's not written there? 10. So I have to have a base. I didn't leave myself much room to write the base. So log base 10 of y. So if the base was 10, it's going to be 10 raised to the x plus 5 power is the inverse function. So if you want to write that as y equals, but y equals 10 to the x plus 5. So it was a base of 10 log, so I get a base of 10 exponential function. See, starting out as a log, ending as an exponential function. Why don't you try number 19 on your own as the last thing? See if you can figure out 19, and then we'll just put it. So I've put it up for when you're ready to look up there